Hello. Now that we know about indefinite integrals, we're going to learn about differential equations today in applied calculus. Now, don't get too worried. There is an entire math course, well, math courses at both undergraduate and graduate levels about differential equations. We are just doing the very basics. And so we're going to learn the vocab of that and realize we've actually already been doing it. So in order to do these problems, I first need you to review for a second. Stop and pause the video for a second and just take the derivative of this function, 2e to the 5x. Easy enough. Okay, so hopefully you got that the 2 is a constant that stays, and then derivative of e, it's the coolest derivative ever, right? It is itself, but with the chain rule, times the derivative of its inside, which is its exponent. Well, the 2e to the 5x part was our original function, and so we have 5 times our original function. And that's really special about the exponential, specifically the natural exponential function. So notice that the derivative ended up being a constant multiple, right? Just 5 times the original function. So keep that in mind in a couple of minutes when we need to think about what function has a derivative that is just a multiple of the original function. So here, let's get the lingo down of differential equations. It might sound scary. All a differential equation is an equation that involves a function, an unknown function, and some of its derivatives. That's all it is. We've already been doing functions involving derivatives. We can talk about a first order differential equation or a second order differential equation. Now we're only going to be doing first order, but you might hear that or see that. And the order of a differential equation is simply the order of the highest derivative. So if you had y prime, that's a first derivative, it's a first order. If you had y triple prime with 3, that's a third derivative, and it would be a third order. Okay? Now, the answer to these questions is a function. And we've already been doing that with those antiderivatives, where we were kind of thinking backwards and saying what function gave us this derivative. So a function f is a solution to a differential equation if, when you plug it and any of its derivatives as needed in the equation back into the equation, you get a true statement. So if it's satisfied when you plug it back in. When we're asked to solve a differential equation, we first are asked to find all possible solutions. And we will have that c involved. We're used to getting that. With those indefinite integrals, we were getting a plus c. We were getting a whole family of functions. And so that family of solutions, family of functions that satisfies what we are asked to solve is called the general solution. So that'll still involve a plus c and is very much like when we did a plus c. But then, back when we were very first learning antiderivatives, we sometimes were given an extra piece of information called an initial value, and we were able to use that piece of information to say, I mean this one out of the family of functions, and solve for c. And so, again, we're doing that. We just have some new language for it. But this we've already used. If we're given an initial value, then this is called an initial value problem. It even has its own abbreviation, IVP, if you were doing a lot of differential equations. And what we end up getting is, now that we know c, we have the particular solution that we were talking about, right? So like when we used an extra piece of information to solve for c. So again, we've actually done this before. We're just now calling the plus c version the general solution, and when we're given an initial value to solve for c, that is the particular solution. So to show you that we really have been doing this already, we have a question that you'll see is what we've been doing, but with the new lingo. So it says, find the general solution of the differential equation. Well, it's a differential equation because it involves a derivative. That's it, differential, right? Differentiate means to find a derivative. So the answer to this problem is the function y, and y will be a function of x, that where its derivative is e to the 0.25x, okay? Well, remember that an antiderivative, right, that indefinite integral, we'll undo a derivative, and notice what happens there, right, with the dx's, and get you back to the original function, okay? So it turns out that this is actually a U substitution problem, right? That doesn't look exactly like one of the only 3 rules we know for antiderivatives, but it's very close to the one involving E, and so we said that we choose the exponent to be our U. So if we let U be 0.25x, then remember that du is its derivative, which would be 0.25 dx. The problem is I don't have a 0.25, so if I put one in, I have to compensate on the outside. And so that looks kind of ugly if you do it how we've been doing it, simply because it's a decimal. So please remember that 0.25 is just a fourth, and so if on the outside I need to compensate for that, 1 over 1/4 is actually just 4 when you do the division and multiply by the reciprocal. So for me to put a 0.25 in here to have exactly my du, I'm actually effectively putting a 4 on the outside, because 4 times 1/4, or 0.25, would be 1. So I haven't changed the problem. Now that I've done that, I have e to the u du. That is one of the nice antiderivatives, I know. And so the 4 is a constant that stays, and the antiderivative of e to the u du is e to the u, and then we get our plus c. And so then, of course, I need to put it back into x's. The u is just to help me with that substitution process, and so I get 4e to the 0.25x plus c. So we just did a u substitution problem here. It just had a different heading, right? Find the general solution, so you still have plus c's involved, to the differential equation. But we were just integrating a function, a derivative here, to get back to the original function, and we used all our same techniques. Here's another one. So if you know the derivative is 13 over x, we're asking what was the original function. That's exactly what we did previously. So we will integrate to undo the derivative, and that means we are simply integrating 13 over x dx. The 13 is a constant that could come out in front, and the antiderivative of 1 over x is the absolute ln of the absolute value of x. So we have y equals, the 13 is a constant that stays, the ln of absolute value of x, and then plus c. And so we are getting these general solutions to these problems. You can see sometimes it'll just be a straightforward problem. Maybe we had to bring a constant out, but that's still very straightforward. Maybe it'll need U substitution. So you can see why we learned that, because those could pop up at any time, and we just need to use what we have in front of us and apply what we have in our toolbox to be able to solve the problem. Okay, so here is one more, and what you'll notice is this time we are asked for both the general and the particular solution. So for the general solution, if I know that there's some function whose derivative is negative 7 x to the 6 e to the negative x to the 7th, then if I want to know what function that was, I will find the antiderivative of it, right? I will integrate dy dx and get what that original function was. So this also, right, does not look just like a perfect little one of our 3 antiderivative rules that we know. And so it is also a U substitution, but it's actually an even nicer U substitution problem than the other one. So here I let my exponent be my u, and then its derivative is negative 7 x to the 6 dx. I got that by taking u's derivative, not by looking somewhere else in my problem, but it is nice that that ended up being somewhere else in my problem. So I have that as my du, and I'm able to substitute. So I now have e to the u du. I find its antiderivative, and I get e to the u plus c, and then I put it back into x's. So we have y equals e to the negative x to the 7th plus c, and that is our general solution. This time we are also being asked to find the particular solution, and we're given an ordered pair. Now this might look a little bit different, but here, since they're saying dy dx, nobody used f as a name, for instance, for the function. So sometimes you'll see y of x. So y is the name of the function, and it takes an input of x. And so this means we have the ordered pair 0, 4, where that input is, of course, your x, and the output is the y. So that might look a little bit different. You may have seen that notation in a science class, for instance, but we usually have had some other name like f or something, but it still works. So that is an ordered pair they're telling you that will help us find the c. Okay, so here was our general solution. we simply use that ordered pair, putting them in for the correct values. 4 was our output, our y, and 0 was our input. Now 0 to the 7th is of course 0, and negative 0 is 0. And so we actually have 4 equals e to the 0 plus c, and we're using that to solve for c. So you can see that if you forgot the plus c in your general solution, you'd have nothing to solve for here. You'd have no unknown. So that should be a hint to go back and fix your work. So we now have 4 equals e to the 0 plus c, but e to the 0 is 1. So 4 equals 1 plus c, subtract 1 from both sides, and you get that c is 3. So then we put it all back together. We combine that general solution with what we now know c is to get our particular solution. Y equals e to the negative x to the 7th plus 3 is our particular solution. So we want to head in, those were just putting different directions to things we've already been doing to help you see you've been doing differential equations, so the title doesn't need to scare you. But we're also going to see that we know what the format of the answer will be to a lot of these problems. And this is where our review is going to come in. So this says find the general form of the function that satisfies this equation that the derivative of p of t, right, the derivative of p with respect to t is 3 times p. So this says there is a function p of t. I know it's p of t because this is dp dt, so that's my input, whose derivative is or equals a constant multiple of, so 3 times as a constant multiple of, the original function p of t. Okay? So if you go step by step, the derivative equals a constant multiple of, or constant times, the original. Where did we see that? So remember back at that warm-up exercise, we took a derivative, not an antiderivative, to recall something neat about the natural exponential function. So the natural exponential function, y equals, you could have some constant here out in front, c, e to the, you could also have a constant up there, kx, for instance, or we could have t as our input variable, is the only function whose derivative is simply a constant times the original, okay? So we have learned that in the past. It's the coolest derivative. So now if we are told that the derivative of some function is a multiple of the original, we know that the answer, the function that's a solution to that differential equation, must have the form y equals c e to the kx. So what's going to happen for most of these problems from here on out is they're going to tell you that the derivative is a constant multiple of the original, and you automatically know what the answer looks like. It looks like y equals some constant e to the kx. And where does that k live? We're about to find out. So going back to this problem, it's going to have this look, and remember it was p of t, and I got that from the dp dt, is some constant times e to the, and it turns out that's where the k comes from. So that constant multiple of the original function that they told me about ends up being what's up here. And you'll see why when we check our work. So if this is the right answer, I should be able to take its derivative and see that it's 3 times this answer. So what is the derivative of this function? C is a constant that stays. The derivative of e to the 3t is itself times the derivative of the exponent. And c e to the 3t was our proposed function, p of t, that we think is the answer. And we do indeed get that the derivative would then simply be 3 times it. So because of how the chain rule works with exponentials, that is why that constant multiple that they told me about ends up being that multiple up in the exponent. So now we'll know whenever they give me this, that the 3 or whatever multiple is there ends up being the variable up with our input variable, the number up there with our input variable. So here, if we are told that the derivative is a constant multiple of, in this case, negative 0.3 is our multiple, y is the original function, right? So the derivative is a constant multiple of the original function. we know the format of the answer. It is y equals c e to the k, in this case x, because I'm told my input variable there. So I automatically have my general solution. Y equals c e to the, right, k is that negative 0.3. Whatever that multiple is becomes our k. Now what you will notice is that where our c is in a different place than when we first learned antiderivatives. You were used to seeing it as plus c. It does have that same use here. It has to do with the fact that if I put a plus c up in an exponent, rules of exponents would break it apart, and e to the c I could just call another constant c, and it gets multiplied. So it is the same idea of that arbitrary constant. This is just what it looks like for an exponential. So now that we know that the only function where the derivative is a constant multiple times the original is y equals c e to the kx, where k is that constant multiple, you can immediately write the general solution to one of these problems. So that is something that you're going to need to know, and it's kind of a if this then that, right? If it looks like this, then the answer looks like that. And so you do have to get that down, but it's not too difficult. Then, this is the general solution, but it also said to find the particular solution. So to find the particular solution, I have to use what they gave me. So again, they gave me this y of 0, and that's because the only things mentioned here are y and x, and y is a function of x. So this 0 is my x, and the output 60 is my y. So I have 0, 60, and I use that to solve for c. It's just I know our c lives in a little different place than when we had polynomial functions, now that it's an exponential, but it is the same idea. 60 is the output, equals c e to the negative 0.3 times 0 was my input. Well, negative 0.30 is 0, and e to the 0 is 1. So 60 equals c times 1, or 60 just equals c. Now what you're going to see is that anytime we are told our y-intercept, also known as our initial value, the y value when x is 0 or t is 0, depending on your variable, anytime we have that 0, for instance, p sub 0 is one way we talk about an initial population or initial principal in an account, this will happen because e to the 0 is 1. We will find out that our c actually is that initial value. So that's going to be the one more piece where we really are going to be able to go straight into our particular solution as well. So we found out that c was 60, and so our particular solution is actually y equals 60e to the negative 0.3, where that was our k, times t. And so now that we've made this observation, anytime they tell you the output when your x is 0 or your input is 0, you immediately know what that c is as well, that it is that initial value, and you'll be able to write the particular solution. So I know this is small, but I'll highlight it for you. I still wanted it all to be presented to you. So this, if we have the derivative is equal to a positive multiple times the original, we said that k ends up being the same k in the solution, that y equals c e to the k, in this case t. And then if we are told information about when x is 0, what c is, then c is by definition the initial value and ends up being that constant that's there. It's not just any arbitrary c, it ends up being the initial value. And so that would be your c, whatever your output is when when x is 0. And then you can see that because it's an exponential, it is going to grow. And so applications of this would be, it's uninhibited population growth, so that isn't really realistic for the long term because there's always something that would limit your growth, whether it be space or food supply or predators. But for short term, or talking about money compounded continuously, and we have already talked about that, and then price supply curves as well in our business applications. Then if we are decreasing, we call that exponential decay. And in this case, what you'll see is it's a negative constant that's being multiplied by your original function, and that negative will also show up. So if you just take the exact constant you see and put it up there with its sign, you'll be good. And then c, of course, is still that initial value. So it's the initial value, e to the k, with its sign, times your input variable. Now if it's decaying, and we have a negative exponent on an exponential, it's going to decrease. And The one main place you might have heard this is in a science class with radioactive decay. So if you have 500 grams of a radioactive material, it decays at a rate proportional to how much there is. So the more there is, the quicker it decays. And then as you get less, then it slows down its decay. And so that's why it's steeper and then levels off. And then we have a business application of the price-demand curve. And then they've listed a couple other kind of science applications there as well. So you can see that whether that was a negative or a positive, what we do is the same. We just carry the negative with it. But if it is a negative, we are decaying versus growing. So this is what an application problem would look like. And you can definitely expect to see something like this or one of the following problems on your test and final. And so they do give us that P0 is that initial amount invested, and we've talked about that before, and it is compounded continuously, so that's a hint right there that we're involving E, but then this is it as well. And it's growing at 6.8%, and you can see this is 6.8% in its decimal form, 0.068. So they are telling us that the derivative is a constant multiple times the original. And whenever that happens, then we know the format of the answer. It is that P of t must be the initial amount, P0, e to the k, where this decimal form, in this case of that percent, 0.068, is our k, and then times t. So if you know that 500 was the initial investment, you can immediately write the equation. So the answer to part A is just a function, and that's what I'll ask you as well, to say, get ready, write the function, then we'll use it. So for part A, I know it's P of t because of this. Even if it's just said a big P without the of t, I would know it's P of t. And it equals the initial amount, e to the kt, where they told me my initial amount was 500, and my k is given here. So 500 e to the 0.068 t. That is all I'm asking for in that question is part A, just find the function. It'll still have variables in it. Then in part B, what is the balance in the account after 3 years? What do you think you're doing, right? You're just using that function, and our t is our time, so we are simply letting t be 3 and using our calculator. So P of 3 would be 500 e to the 0.068 times 3. We do need to remember our careful typing from previous sections, where we will type 500 times e caret parentheses 0.068 times 3, then close the parentheses, and not use parentheses as our multiplication, but actually use a multiplication sign so that both of those stay up in the parentheses. When you type that, remember any money question, you should be rounding to 2 decimal places without being asked for me on a test. And then follow the directions in the homework, but normally it will say 2 decimal places as well. So this may have involved rounding, but I end up with $613.15. So if I put $500 in this account for 3 years at this interest rate of 6.8%, I will end up with $613.15. So then using that same scenario, the question is, when will that money have doubled? When will that initial investment of 500 have doubled? Well, I know this is my function. I wrote it. That's why we did part A, so that we could use it. So in part B, we just plugged a t into it. This time, we're told something about the output, and we don't know t, right? When, the question word is when, so I don't know the time. I don't know t. But I'm told that it's going to double itself. So that means that my output should be 2 times my input. Now, of course, you can probably think 2 times 500 is 1,000, and you are welcome to write 1,000. There's a reason I didn't, but you can, right? So 2 times 500 is 1,000. You could write 1,000 equals 500 e to the 0.068 t, and we're trying to solve for t. The first thing I have to do, and we practiced with this back when we reviewed derivatives of exponentials, is to get the quantity with the t in it by itself by dividing both sides by 500. So yes, this could be 1,000 divided by 500, but you'll still get 2. And I was just showing you that that's going to happen anytime you're asked a doubling question, that you'll get a 2 there. So now we have 2e to the 0.068t. Now remember, If I have a variable stuck up in an exponent, I have to use the inverse of an exponential, a logarithm, to get to it. And so in this case, it's the inverse of the natural exponential, which is the natural log ln. So I am taking the ln of both sides. I'm not multiplying both sides by ln. That doesn't have any meaning. I am doing ln of 2 equals ln of e to the 0.068 t, because the ln and the e are inverse functions that will undo each other, giving us just the exponent 0.068 t. Now, to get t by itself, I simply have to divide. So I will divide both sides by 0.068, and when I type, I need to be careful to say ln of 2, close the parentheses, then divided by 0.068 to get what my t is, and then round as you're told to round in the problem. So we end up getting about 10.2 years. So if I have $500 in an account earning 6.8% interest, compounded continuously, it would take 10.2 years for it to double its value and get to 1,000. So let's look at one more. Now this one, it looks like it's a lot more difficult because we can't immediately write our function. However, the work we need to do to write our function is actually just like the work we just did a second ago to solve for t, because what we're going to have is that our unknown is stuck up in an exponent. So the difficulty level is actually no different than what we did before, and we actually did in a whole previous unit when we were reviewing e and taking derivatives of it. So they tell me information about that marginal price, right? Marginal means derivative. So dp dx, where x is the units of demand per week, and then of course p is going to be a price, it's going to be money. And so we have some facts about it. And we have observed from running our business these facts, and then we can use that to build the function, that there is no demand if we have a price of $150 per unit. Nobody's willing to pay that. But there's a weekly demand of 6 units of our product if we lower the price to 126.97. So that gives us some data points that we can then build a model on, and that's what we're going to do. So the first question is the same as our last problem, where please write the function. The problem is this didn't tell me the relationship between the derivative and the original, what that constant multiple is. Instead, it gave me 2 ordered pairs. But one of those ordered pairs is the initial value. So I do know that this is going to have the look of y equals c e to the k x, and I know that that c is my initial value, so I already can write the basics of our function. What I'm missing is k. So I have p of x equals 150 because that was our initial value, e to the kx. And then I will use the other piece of information that I was given, the fact that p of 6 equals 126.97, to solve for that k. And that is the ordered pair 6, 126.97 as a reminder. So I will replace my output with 126.97, replace x with 6, and that leaves just my unknown variable k. And so while in this case we are solving for k, not x or t like we were last time, because they live together up in that exponent, our steps will be the exact same. I absolutely must first divide by 150 to get the quantity with the variable in it, the e to the 6k or k6, by itself. So I have to divide off the 150 first. Now you could type that in and get some crazy decimal. If it's a terminating decimal, fine, but write all of them. Honestly, if it's a decimal that goes on for a long time, it would be much better for you just to leave it and type it in all at once than it is for you to randomly decide you should chop it off at 1 decimal place or 2 or 3, because that can get your numbers quite off. All right, so I'm just leaving it, whatever that equals, we'll see in the end. And now I have e to the 6k. So I need to undo that e with an ln. So I've taken the ln of both sides, and the ln and the e will undo each other and give me just that exponent part, the 6k. And then to get k completely by itself, I need to divide by 6. And so I would type this in all at once, and then I don't have to worry about any rounding issues. So I would type ln of 126.97 divided by 150, close the parentheses, then divided by the 6. Okay? And what I get is negative 0.02778. And so what I've done is, instead of trying to figure out was it going to be increasing or decreasing from the beginning, I just did the work, and so there's my negative sign that I need for the problem. So I just put it all back together now that I know my k, and p of x is 150. We already had that from the beginning. E to the, now I know my k, negative 0.02778 times x. So that is more difficult in writing it, but it's actually the same steps we had done in a part C of another problem. So it is no more difficult than that. But I just had to solve for my k in order to now have my function. Then they'll ask me to answer questions about it. So at a demand of 10 units per week, what is the price? So now that you have a function, use it. And if you go back and read the problem, it says x was the units of demand per week. So they're telling me an x, and I'm simply plugging in. So to recap from the last part, p of x was 150 e to the negative 0.02778x. And now we're told that x is 10. Can you please tell me the output, right? So we just replace x with 10, carefully typing. 150 times e caret parentheses negative 0.02778 with a multiplication sign times 10, and then close your parentheses. And you will get something like 0.615, and so we should round. And so we have $113.62. So if you want there to be a demand of 10 units per week, you would need to price it at $113.62. So one more example. This one, I guess that one actually ended up being a decay problem as well. This is about radioactive decay. And so you'll notice that you see the negative sign in the problem, and that is because it's this radioactive material that's decaying. And so you know that the derivative is a constant multiple times the original. You automatically know the look of the answer. It is going to be N of T equals your initial amount, which they told me was 500, e to the k, including its sign, so negative 0.096, and then times input variable was t. So do notice again that part A is simply asking you to write the function. So that's all I'm asking you to do there, and then that'll make it so that you have it ready to use for other things. So N of t equals 500 e to the negative 0.096t. Now we're going to use it. So in B, it says how much will remain in 4 days. So remember that this function does model how much is left after that amount of time, not how much you've lost, okay? And so 4 days, that's a time. And so I'm just replacing t with 4. That's it. So I take my function that I just wrote, and I plug 4 into it. So if you have a reasonable but incorrect function that you wrote, but then you plug 4 into that function as your t, and you understand that that's what you're supposed to do, I will still give you full credit for this part of the problem. So even if you're questioning your work on an earlier part, go ahead and do what you would do with that to show me you know, and I will give you credit for that. So we end up getting 340.57 grams would remain after 4 days of that radioactive material. And then lastly, after how many days will 500 be left? So, will half of, okay. So lastly, after how many days will half of the 500 grams be left? So half of it left. Now, if you think about it, you have probably heard about a half-life of one of these radioactive materials, or even a half-life of a medication, and how quickly your body processes it. And that's exactly what we're talking about here. So this is much like part C 2 problems ago. I want to know when half of 500, so you could write 250, or you could just write 1/2 of 500, is left. So how long will that take? How many days will that take? So how many days will that take? That means that t is our unknown. That's what we're solving for. We know that we want half to be left. That's our output. So 1/2 of 500, when does that equal? 500 e to the negative 0.096t. Again, I must first divide the 500 off. And again, you could have written 250 and you would get the same result, but just to show you that that's happening, you do get a 1/2 here. Then to get to the variable stuck in the exponent, I need to apply ln. And so I have ln of 1/2 equals, and I'm left with just what's up in the exponent, negative 0.096t. And lastly, I need to divide by that constant, negative 0.096, to get t by itself. And so I do need to type carefully, and again to close the parentheses before I divide by the negative 0.096. And it might worry you, I'm going to show you on the next slide, it might worry you, it might look like this is going to be a negative answer if you just glance at it. And it's time, so it probably shouldn't be negative, but if you do type it into your calculator, you will see it is a positive number, 7.22 days. So it would take about 7.22 days for half of that material to be left. So in that example, what we were looking at was called a half-life, right? We were finding the half-life of that material. And then just to address the fact that at a glance that looks like a positive divided by a negative, remember that our laws of logs say that ln of the numerator, if you have a over b, it's ln of the top minus ln of the bottom, and that ln of 1 is 0. So what I have in the numerator here is ln of 1 minus ln of 2, but ln of 1 is 0, so I actually have negative ln of 2. And so it really is a negative divided by a negative. You just didn't see it because it was kind of hidden in this notation of logarithms. And the negatives cancel. Ln of 2 is a positive value, and so it does end up being a positive number. But if you kind of glanced at that and that worried you, it actually does go back to laws of logs that you had learned before. So with the majority of these problems, our early problems were just showing you this is what we've already been doing. So instead of saying, please find the antiderivative of, it just said, if dy dx equals this, tell me what y was, but with same process. And then in our later problems, which you can definitely expect something like that on the test, it was word problems, but they tell you the relationship between the derivative and the original function, and you automatically know the basic look of the function, where the c out in front is your initial value and the k is that multiple, and with its sign included, of the original function that the derivative equals that they told you. And then once you have your function, it's stuff that we reviewed back a couple units ago. I can plug in an input and find the output, or I can tell you an output and you have to solve for the input, and that involves an ln to undo that exponential. So differential equations really is just a fancy name for some things we've already been doing, and does not need to be something that you fear, and maybe you'll go on to take that class at some point, but for us in applied calculus, that's the extent of what we're covering of differential equations.